So as for any independence, one of the fundamental things that we look at are limit theorems such as the central limit theorem. And if the operator value setting, this one also established. And in order to do this, I'm going first to introduce what are the non-commutative distributions in the operator value setting, how they are defined, and then show you how we can obtain such very So the last part will be on the multivariate setting. So the probability spaces that we consider in this case are the operator value probability spaces, which is a tuple A, E, B, consisting of the complex algebra A with a unit 1, and a unital complex subalgebra B of A, which is unitly embedded, and the conditional expectation, which is takes values in A, and that is a unital DB bimodule mass defined these two conditions. So we call an operator value probability space to be an operator value C-star probability space. In addition to this, A and B are C-star algebra, and E is positive math. And we call it an operator value W-star probability space if the we say that it is a W-star probability space if in addition A is a tracial W-star probability space and B is a von Neumann algebra. And in this case, we can find a conditional expectation E that preserves the trace. Now this is not working. So we would like to investigate the central limit theorem in this case. And this was originally done by Kolmogorov. So if we assume that Xi is a family of self-adjoint elements that are free with amalgamation over B, that means that they are free with respect to expectation E. And we assume that they are centered with respect to E, and we consider Xn, which is 1 over square root of n of their sum. So what Kolmogorov proved is the following. If we assume that all the operator valued moments of Xn are bounded in norm, and if we assume that 1 over n, the sum of the variance of each of the Xi's, this variance map converges to some eta of B, which is linear from B to B, then under these two conditions, Kolmogorov has proved that Xn converges in distribution over B to an operator valued semicircular element whose variance is given by the variance map eta. So there are many things that I haven't defined here that I will come to give their definitions precisely in the coming slides, like these operator valued moments, and what do we mean by convergence in distribution over B. Just note that in this, of course, in the classical case, this we have convergence to the Gaussian distribution. In the free case, we have the semicircular element appearing in the limit. In this case, we have an operator valued semicircular element. And now the variance of this element is not a scalar anymore. It is a mapping. So I will come to give more definitions in the coming. So what we're interested to do in this talk is to give quantitative estimates for such limiting theory. So the approach that we're gonna follow is the following. We're gonna consider two families, X1, Xn, and Yn, Yn. And everything we assume to be free with amalgamation over B. Okay, and we would like to compare the distribution of these two sums under the conditions that the first moments and the second order moments match. Okay, so we consider a family Yn freely independent as well with amalgamation over B. We assume that they are also centered, and have matching moments of order 2 with the xi. And we're gonna look if compare the distributions of these two sums. And then if we can approximate the distribution of these two sums, then we choose dy i's in a way that we can say that this is gonna give us the distribution of an operator valued semicircular. So first we do this approximation, and then we choose dy i's in a convenient way. So what are distributions? We've seen them in the mini course by Harry Berkovich. I'm gonna recall them quickly. So the non-commutative distribution of x is the collection of all moments. So this is in the scalar setting. And we've seen that if we have a self-adjoint operator, then we can describe this combinatorial object here and using a probability measure, a real probability measure mu x that has the same moments as x. So mu x is called the spectral measure of x. And when we are dealing with probability measures, then we have access to lots of analytical tools. One of them we've also seen that it is the Cauchy transform. So here I'm going to denote by gx of z to be the resolvent of x at point z. And the Cauchy transform, it is phi of g. And we've also seen earlier that this Cauchy transform, the pointwise convergence of the Cauchy transform is equivalent to the convergence in distribution. And more precisely, an important feature of the Cauchy transforms is that it characterizes the distribution. So once we know the Cauchy transform, we can obtain mu. Now, in the operator valued setting, how are these distributions defined? So the b-valued distribution of x, it's again the collection of moments, but this time the b-valued moments. So it's the collection of all possible b-valued moments of x. Again, this is a combinatorial object. And we're going to denote by mk of x the multilinear map that gives us these the moments of x, okay, the kth moment in these elements b1 to bk minus 1. And we say that xn converges to x over b, like in distribution over b, if we prove that all b-valued moments converge in norm, okay? And also we have a notion of operator valued Cauchy transforms that are defined now on the upper half plane of B, okay? And they are defined in the same way, but here we have the yes.
So by upper half plane, you just mean elements.
Yeah. So here the elements be the general process. But in this case, in order to prove so that the Cauchy transform give us convergence in distribution over B, it is not enough to prove that E of xn converges to E of x in norm, but we need to prove this for implications of xn in order to capture all these mixed moments in B1. Okay, so we need to prove this for all k. Okay, so we go back to our setting. We would like to compare the distributions of these two sums. So the kind of bounds we are interested in are of the following. We want quantitative bounds on the Cauchy transform of the difference of the two, but also on all amplifications. And we're also interested to get bounds of this term, of this type, on the scalar valued Cauchy transform. And these bounds I'm going to show you later. They're going to allow us to obtain quantitative bounds on the level of the Levy distance and the Kolmogorov distance. So we have two goals to obtain bounds of these two forms. So this is how we're going to proceed. So this is what I said. We choose dy i's to be free with amalgamation and have the same moment up to order 2 as the xi's. And then what we prove is that the Cauchy transform, the operator valued Cauchy transform of xn minus that of yn in norm can be upper bounded by the inverse of the imaginary part of B in norm to the power 4. And this A of X, this is a term that depends merely on the moments of order 2 of X and of order 4 of X and Y. Okay. So this bound here is merely in terms of the moments of order 2 and 4. And of course, we're gonna extend it to all amplification. I'm gonna tell you later how do we obtain such bounds. And also bounds of this term on the integral bounds on the scalar valued Cauchy transform. And again, our bounds are in terms of the moments of second and fourth. So how do we obtain such bounds? We're going to approximate the Cauchy transform of Xn by that of Sn. So we write it as a telescopic sum. So we're going to replace each element of this sum of Xn by an element of this sum Sn in n steps. So at each step, we're going to replace one element by the corresponding one, and we're going to control this this arrow. Okay. Yeah, it's wires. I here I put it as n because at the end we're gonna choose the yi's in a way so that this is a operator value symmetry. But so far this is our YF. So notice that here we denote by Zi. How do we write this telescopic sum? So Zi we sum from x1 up to xi, and then from the I plus 1 coordinate we have the yi's. So notice that here Zn is equal to Sn and Z0 is equal to YF. Sn. And now we're going to introduce another Zi0 where we replace the I component by 0. And now Zi minus Zi0 is xi. And this is independent of Zi0. Okay. And similarly, Zi minus 1 minus Z0i is equal to yi. And this is independent of Z0i. And what we're going to do is we're gonna control each of these terms separately because they are done in the same way. So we expand this using this algebraic identity. Okay, so this is the resolvent identity. We develop it up to order 3. So what's important here is that this term only includes Z0i and xi, and they are freely independent. So we have the xi here in between is freely independent of the Cauchy transform of the resolvent. And the same for the second order term. We have these terms that are the xi's that are independent of all the others. However, in the third term, we have zi, and zi contains xi. So here we don't have freely independent terms. So we're going to control the first two terms alone, and then we're going to find some estimates on the third one. So for the first one, if we take now the conditional expectation, this is going to be xi. G of Z0i. So this will factorize in this way. We will have expectation of EI here, and as it is centered, this will be 0. And for the second order term, we're going to have Z0i of B xi G Z0i. And if we take the expectation, we will factorize in this way. So this element here, it is in B. So this term in between, this is the second moment, okay? And as we have assumed that the second moments match, so this term from the first term here is gonna cancel up with the second term there, because we will have instead of the xi's, yi's, and we have assumed that the second moments match. So this is how we prove that the first two terms cancel. As now for the third term, we need to, in order to obtain moments in our bound, we have to get rid of this term here where we have independence. So we use the positivity of the conditional expectation. And then we will obtain, we get rid of it, we take it out. And then we only have terms including xi and g of zi0 and that are freely independent. Then again, by the moment equivalent formula, we can factorize and obtain bounds in terms of the moments of second order and fourth order. So this is a glimpse on the proof. And in order for the integral term, we have to be also a little bit more careful because we would like to obtain in our bounds the norm of the Cauchy transform, the L2 norm of the Cauchy transform square. And then we're going to use the fact that 1 minus 1 over pi, the imaginary part of the Cauchy transform, is a probability measure, so that we prove that this integral is finite. So this is on the level of the proof. Now let's apply it to the central limit theorem. So before I wasn't normalizing. So here xn was just the sum of xi's. Now we're just for the central limit theorem we normalize by 1 over square root of n. And we choose the yi's to be operator valued semicircular elements, matching moments with the xi's, and we set Sn to be 1 over square root of n, the sum of the yi's. Now we know that this Sn is itself an operator valued semicircular element, and we can easily compute its variance. So applying our theorem, we prove that the distribution, the Cauchy transform of xn is compared to that of Sn in this way. We have order of 1 over square root of n. And here again, so the n that was there, it will be killed. Okay, and we obtain 1 over square root of n. And we have here bounds in terms of the moments. And then we can relate the moments of the yi's to those to the xi. Okay. So what I would like to say out of the theorem is that the bounds do not depend on the operator norm, they depend on the moments of order 2 and 4. And we don't need to prove to repeat the proof for the amplified version. We just change our framework. So if the x1 up to xn are freely independent over E, then their amplification is freely independent with respect to the identity tensor E. So we just change our probability space, and then we obtain the above result. And we obtain this bounce, but with k to the power 3, but this is not harmful because k is. And so if we assume that Sn is independent of M, like, for example, if you assume that the xi's are identically distributed, then in this case, Sn is itself an operator value semicircular element and does not depend on n, the variance. Then in this case, we prove that xn converges to S, to the operator value semicircular element over B. But what if we don't want to assume that? We don't want to assume this, and we would like to obtain a Volkowisko's result. So we have this additional step where we prove that if we have two operator valued semicircular elements with different variances, eta 0 and eta 1, then we can compare their Cauchy transform here. And the upper bounds we obtain are in terms of the norm of eta 1 minus eta 0. So here we don't have, we follow the same steps, but here we don't have that the second order moments match. So this is why this term here appears. And now under the same assumption that Volkowisko had, we have that this norm here converges to 0, and we obtain the central limit theorem. Okay. And now if we would like to obtain bounds on the level of the Levy and Kolmogorov distance, I'm first going to recall them. So we assume that f mu is the cumulative distribution function of a Born measure mu. We denote it by that. And then the Levy and Kolmogorov distance are defined this way. So I assume that most of you are familiar with them. So some properties of on these distances. So the Levy distance can be upper bounded for any epsilon positive by 2 square root of epsilon over pi plus 1 over pi, and this integral that I was before interested in. So once we have quantitative bounds on this integral. We plug them here. They will be in terms of epsilon and n. And then we optimize over epsilon to get our quantitative bounds on the Levy test. And another property. So this is how the Levy and Kolmogorov distance are compared. So this first inequality always holds. But if we assume that f mu is Holder continuous, then we can upper bound the Kolmogorov distance by the Levy distance, and we have this beta exponent here. So this is on these distances. So in the classical setting, we have this quantitative bound on the central limit theorem in terms of the Kolmogorov distance. Of course, here the limiting distribution is the Gaussian. And we have 1 over square root of n as speed of convergence, and epsilon n is the, and m3 is the absolute third moment. So this is given in terms of the moments up to order 3. In the free case, we have also the moments of order 4 that appear, but we have the same rate, square root of n. And now in the operator value setting, we're going to use our bounds on this integral of the difference of the Cauchy transform to obtain the following. So this is what we get when we normalize. So we get that this integral term is upper bounded by 1 over square root of n times this term, which includes the moments of second and fourth order. And once we use the bound I showed you before and we optimize, we get this quantitative bound on the level of the Levy distance. So we're not claiming that this n to the power minus 1 over 14 is optimal, but it is the first quantitative bound and the operator value. So, okay. Now, if we assume that we have Holder continuity for f mu of s, and that Sn is independent of n, of course, then by the we can upper bound the Kolmogorov distance by the Levy distance to the power beta, so we obtain this bound. However, if we use an earlier result in 2019 of myself and Tobias mine, we can obtain a slightly better bound once we have Holder continuity than this one up. But the advantage of this bound here is that it always holds without any assumption on the distribution of the operator value semicircular element. So it can also have atoms. And we still have this bound on the Levy distance. However, when we know a little bit more, so we can obtain slightly better bounds. I've showed you the results so far only on the level of for the central limit theorem, but I just want to point out here that they can be applied to more general things. So if we consider this matrix whose entries are operator valued, okay, so this is a self-adjoint matrix, and AIs are assumed to be freely independent. They are self-adjoint on the diagonal, and we complete it here by symmetry for the of diagonal entries. So we can write this matrix in this form. So we simply consider the unit matrices, and we write it as the sum of these unit matrices tensors the AIs. And we note that if we call this term here xij, we have that those xij's are now freely independent with amalgamation, but with over mn of b. So here we just change our framework, but we still have the sum of freely independent, but now we are in the operator valued probability space consisting of matrices whose entries are in A, and with the conditional expectation being the identity. Okay. And we are still in the same framework. And if we have that these AIs are centered with respect to E, then the xij's are also centered with respect to the identity tensor E. So we can repeat the same thing. And now we choose our yi's to be semicirculars on the diagonal and circulars on the off diagonal. And we assume that they are all freely independent with amalgamation. And then we construct this matrix Sm using these semicirculars and circular elements. And we know that this Sm is itself an operator valued semicircular element over the diagonal matrices with entries in B. And the variance map can be computed easily. And this is how it looks like. Okay, just want to tell you that this is a general thing. We change our framework and we decide how to choose the yi's. And now what about in the last part of, so I didn't state the theorem, but it just follows. We have the same rates of convergence and everything, just saying that this applies to matrices as well. So now what in the time remaining, I'm going to talk a bit about the multivariate setting. So now if we consider tuples, x11, x1d, to xn1, xnd. So the tuples themselves are freely independent, but here inside each one, we allow correlation. And we're interested to study the non-commutative joint distribution of xn. Okay? Again, one under these conditions that they are centered and when we don't take the self-adjoint, this is. So what is the non-commutative joint distribution in the operator value setting? It's defined in a similar way. So it is the collection of all B-valued moments, but in this family. So all mixed moments in these elements here. Okay, and the distribution is just given by the collection. And now we have to modify more our moment function map. And again, we say that this converges in distribution over B if we can prove that all moments converge in O. Okay, so it's similar to before. And in this case, the central limit theorem was proven by Speicher, who, under the assumption that they are identically distributed and centered, proved that Xn converges to this family of circular elements over B. So this is a family of B-valued centered circular elements. And now notice that the variance is given by two maps, eta and eta tilde, that distinguish the order because we're no longer in the tracial setting. And here the map is from B to MD of B because we have correlations. We have tuples of B elements and we have to consider their correlations. So the K-elf matrix entry will be giving us the correlations between XIK and XIL, and similarly for eta. So again, we would like to derive quantitative bounds, but to obtain quantitative bounds, we need to go to analytical tools, but it's not clear if we have more than one element, how to describe the distribution using measure theory. So the best we can do is to consider test functions in these elements. Okay, so we would like to study the joint distribution of these guys here. We take a test function f of them. We choose it to be self-adjoint. So now we are in the setting of one self-adjoint element. And here we have access again to measure theory and analytical tools. So, and the idea is that the larger the class of test function is, the more information we can obtain. So we consider two classes of test functions. The first one is matrix linear pencils, which is linear in the elements, but has matrix valued coefficients. And the second class of test functions will be B-valued non-commutative polynomials, and these indeterminates x1, x1 star up to xd, xd star. So let's consider the first case, start with the matrix linear pencils. So we consider G of xn. Okay, it is written in this way. We would like to collect all the correlated elements together, okay, in a new element x till j. So these xjl, if we sum from L equal 1 to D, these here are correlated. However, when we change the index G, then they are freely independent with amalgamation. So again, we write this G of Xn as the sum of freely independent elements with amalgamation, but this time with respect to the identity tensor E. Okay, so we start with tuples that are freely independent over E. When we consider the matrix linear pencil, the free independence lifts to the level of the matrices, but this time with respect to the identity tensor E. Okay, and again, we can simply prove that they are still centered with respect to this new conditional expectation. So we are again in the framework of one variable in the operator valued setting. So we can obtain results on the multivariate setting by doing this and applying the results for the one variable setting. And again, we choose the yi's to be operator valued circular elements, matching moments. You know the story. We set Cjk to be their sum. We know that this guy here, it is an operator valued circular element. And we can obtain a quantitative version of the central limit theorem by this way. So now we know what are these Cn1, Cnd. We apply our theorem and we prove that, again, we have this 1 over square root of n, but of course here we have a constant C that depends on the linear pencil on these matrices Q. And in similar way, we can obtain upper bounds, quantitative upper bounds on the level of the Levy distance. So we just cut from the multivariate setting to the one variate setting this way, and the results follow directly. And then if we assume in addition this condition here on the distribution of G of these circular elements here, for instance, we assume that they are identically distributed, IID, the CIs, then we can recover the multivariate central limit theorem and the operator values. Now, what about the polynomials? So here, it's a bit different story. So if we consider polynomials in these elements, so they are it is the C linear span of monomials of this form. And we would like to look at the distribution of P of Xn. So here we have lost linearity, which is an essential ingredient for the Lindeberg method. So we cannot just go back to the one variate setting as we did for the matrix linear pencils. We need to treat it separately. But now we have very well-known techniques to do that, which is the linearization technique. So if we have a polynomial P, we can find a linear representation of it, which is a triple UQV, with the Q being this linear pencil, okay? And we can write P as minus UQ, so U is a row vector, okay? Q inverse V. Moreover, we can choose this representation to be self-adjoint. So this Q to be self-adjoint, and we choose U to be equal to V. We can have such constructions. We denote by delta of B to be this matrix having B on the 1, 1 entry and 0 elsewhere. And Q hat 0 to be this matrix. And here we have the Q hat J's to have the QJ's here and 0 in the upper. And then we construct P hat as this linear pencils and the Q hat. And now we have a linear polynomial in our xi's, okay? But with matrix valued coefficients. So we passed from a polynomial where we have nonlinearity to a linear polynomial, but the price we pay is that we have now matrix valued coefficients instead of complex. And why is this interesting? It's interesting because we can recover the Cauchy transform of P by looking at the 1, 1 entry of this matrix here. Okay. So we consider the resolvent of P hat at point of B, and we look at the 1, 1 entry. And once we pass to this operator valued level, we we find our estimates that we want to find, and then by taking the 1, 1 entry, we can pass them to our or initial polynomial P. So this has to be treated separately and not as, even now with the linearization, we cannot apply the result before, because this LP of B inverse is not an operator value Cauchy transform. This delta of B is not in the upper half plane. Okay, so we need to treat it again separately. But we obtain still the same kind of results, but here with an additional term mx, which is 1 over n, the norm of x plus the moment of order 2. So we have now the operator norm appearing in our estimates, but it's not in the leading term. So the leading term here is the moment of order 2. And again, we obtain 1 over square root of n as the speed of convergence. Okay, so this is, I'm telling you why, from where this comes. This comes when we're controlling the norm of this LP matrix. And now some of you might ask the question, why did you do that? Why didn't you consider delta epsilon of P, where you put I epsilon here, and now this is in the upper half plane, and this is an operator valid Cauchy transform. And then we apply the result from the one variate setting, and so this is possible. But at the end, we will obtain bounds in terms of epsilon and n, and we would need to take this limit. So we would lose on the level of the speed of convergence. So we chose to have the operator norm appearing as a non-leading term, but keeping this 1 over square root of n from doing this and applying directly the result. Yeah.
B of xn is a function of x.
Yeah. It was called A, now it's called B. it's similar. It's not exactly the same one, but again, it's a term including only the moments of order 2 and order 4. Okay, it's not exactly the same one. That's why we changed the notation.
Is there something interesting about the all of it, or is it just something?
No, here you're just taking like a sum of different terms depending where you have the x or x star. Just because here you're dealing also with non-self-adjoint alpha. Before we were considering self-adjoint alpha. So, but it's like only including moments of order 2 and 4. So yeah, this is what I wanted to say on for the polynomials. And again, we can obtain bounds on the level of the Levy distance. But with this mx, that includes the operator norm as non-leading term. So here I should cite some people because I didn't mention anyone. So on the multivariate central limit theorem, there were many results before, for instance, by Speicher and Mai, who treated the multivariate IID central limit theorem, and by the entropic non-microstate IID central limit theorem, Fatih and Nelson, but from an entropic non-microstate point of view. And Jekyll and Leo, who have a central limit theorem for T dependencies, like they obtain the same speed of convergence, 1 over square root of n, as we obtain, but their bounds are only on the level of the operator norm. Their estimates are on the level of the operator norm and cannot be passed to obtain bounds on the Levy and Kolmogorov distance. So, and as further step is to obtain similar bounds, but for the operator valued Boolean and monotone independence, here is space, and also in the infinitesimal setting, quantitative bounds on in the infinitesimal setting for the free Boolean and monotone independence, and these are projects with Octavio Arizmendi and Pai Won-Sang. So hopefully in the coming month or month and a half, we'll see them on arXiv. And yeah, I think I'm out of time, so I would like to thank you for your attention.